Welcome, NutritionRadio.org listeners. This is Lonnie Lowry, a university nutrition professor of over 20 years and podcast host of long-running shows like Iron Radio. Come on in. Lecture time. Hey, everybody. Today we're going to go back into the classroom for part 2 of the carbohydrate lecture. I know last time I alluded to the idea of showing you how to carb load and that sort of thing. Actually, we're probably not going to get to that till next time. But what we will talk about here in this, 8 or 10 minute clip is more on carbohydrate stores in your body, how we know that things like carb loading works or why muscles store a certain amount of carbs, how we know. If you're curious, this is a good thing. How we make new sugar, right? New blood sugar, if you will, from non-carbohydrate sources, like when you're not consuming any carbs. Why don't you just pass out? Your brain runs on that stuff typically. When you use carbohydrates, how your muscles take them up, when your muscles struggle to take them up, lots of stuff in this one. So let's just go on in there.
If you're going to carb load for sports, how much does that increase? Well, unbelievably, actually. You can multiply up your amount of glycogen stores by 2.5 times when you carbohydrate load. So we'll talk about how to carbohydrate load, but imagine having more than double the glycogen that you normally carry. No wonder runners like that, because they don't hit the wall late in a run. And they actually have more energy during long practices and that sort of thing. More fuel stored. The next slide shows a muscle biopsy. So if you take a biopsy and you slice it real thin, you put it on a microscope. This is an electron microscope. I think this is just very cool. I try to show these sorts of things in different classes. This is muscle under a microscope. Those little dark dots are stained glycogen. And if you look in the sort of in the middle of this slide, you can see little mitochondria, little beads. They look like beans when you slice them like this. And you can see the glycogen's all around the furnace. Well, what a great place to put a fuel, right by the furnace. And this is one of the ways we know, and I'll probably ask you this on a test. How do we know, glycogen gets used up with exercise? Well, if we stained it, if we took a biopsy before and after exercise, we'd see less of it in there. We'd see less of these dark dots. How do we know that glycogen loading, carb loading, it's called glycogen supercompensation. How do we know that works? Well, before and after the carb load diet, we could take a muscle biopsy and we'd see 2.5 times more of these dark dots. So, it's important to me. I know it's geeky, but for you to see it for real. That's not in your book. Next slide is gluconeogenesis. This occurs mainly in the liver. When I was an undergrad, nobody would really take enough time to say, this pathway happens after you eat in your liver. Or in this case, this happens in your liver when you haven't eaten for a long time. Or what happens in your muscles. So try to put it on the anatomical map. This is in your liver, primarily. It's production of glucose from non-carbohydrate sources. And really, these are 3 carbon compounds. So you're not going to turn fatty acids from triglycerides in your diet into new sugar. But 3 carbon things love to go to the liver to make new sugar. Lactate, we discussed already. So lactate and pyruvate are both 3 carbon compounds. They will go to your liver to make new sugar. Certain amino acids can lose their nitrogen and also become new glucose. And this is important because it keeps up blood sugar as the liver gets depleted during prolonged exercise. So once you start to use up your carbohydrates, and we're going to talk about this today, but in about 2 hours, all of your carbohydrates are gone. 2 hours of intense exercise. So how do you keep up your blood sugar so you don't pass out, so your brain can stay fueled? Well, one of the things you do is you keep making new sugar through gluconeogenesis. We talked about the Cori cycle already. I color-coded this slide. You can see lactate is in orange, and so is Cori cycle. The Cori cycle is what happens. That's one of the types of gluconeogenesis. When lactate leaves working muscle and goes to the liver, that's the Cori cycle. And then when certain amino acids do it, that's color-coded in red. That's the glucose-alanine cycle. And we're going to talk more about that in the protein chapter, but just know that there are different kinds of gluconeogenesis. It depends on what you're using to make new glucose. Okay, so let's switch gears a little and look at fuel preferences. Anytime we exercise, we're burning mostly a mix of fat and carbohydrates. At rest, 60 to probably 90% of the fuel is from fat, 60% or more. If you get up first thing in the morning and you lay down on a metabolic cart and you're truly fasted for 8 or 10 or 12 hours, you may see numbers much higher than 60% in the fuel mix. Like 90% of all your calories that you burn in your resting metabolic rate is from fat at that point. 35% from carbohydrates and very little from protein. The relative contribution from fat slowly starts to decrease. So hit the space bar again quickly. And you'll see with moderate intensity, increasing to moderate, fat provides even less of the fuel mix and carbs even more. And then by the time you get to very intense exercise, like you're almost sprinting, then metabolic crossover has occurred. Crossover from fat to carbohydrate as the fuel preference. That's what we're talking about. So let's look at this on a slide. I put on a graph rather. I put this a star on this. This is a very important concept I'm going to ask you about throughout the class. This is from a particular paper from Romine and colleagues, 1993. But this is, you can show this very readily right down in our own lab. At least some aspects of this. So if we look at the bottom of this graph, at 25% of your VO2 max, so very low aerobic intensity, you can see that most of that bar is blue and green. It's muscle and muscle triglycerides and plasma free fatty acids. So you're burning mostly fat. And you can look at the red part is the glycogen. Let's focus on that since this is the carb chapter. A tiny thin wafer of glycogen getting used at such a low intensity. If you go to medium intensity at 65% of your VO2 max, you can see that it's still mostly fat in the blue and green, but now there's more of the red. You're definitely using some muscle glycogen to operate at that pace. And then at 85%, you can see that red bar has gotten bigger than the other colors because you're using mostly muscle glycogen at that point. So let's work with this crossover effect. Next slide is on training and metabolic crossover. Training results, right? Training adaptations shift the crossover point upward. In other words, you have more mitochondria. Mitochondrial density rises, and that increases fat oxidation or fat burning, right? Oxidation is just burning. And that's good. The more fat we can burn, the more we can leave our glycogen stores alone. And why is that good? Because we only have a couple 100 grams of glycogen in our body. We have thousands and thousands of grams of fat, even a very lean person. So the more we can use our fat stores and leave the glycogen alone, that's great because it could delay fatigue. So also GLUT4 increases in just a few weeks. That's another good point. Like I said, GLUT4 are the little doorways, the GLUT4 transporters. And just the act of contracting a muscle will send those up to the cell surface to pull in some sugar. Normally, insulin does that, but just muscle contractions can do that. So imagine how helpful this is to someone with diabetes. You just get them walking or doing some light resistance training, and those flexing and contracting muscles send GLUT4 up to the cell surface to pull in blood sugar. No insulin required in that particular situation. Amazing. I do want to point out the increased insulin sensitivity with resistance training happens except when DOMS is present. If there's delayed onset muscle soreness, those muscles are actually pretty resistant to carbohydrates. Nothing to worry about too much, but if you work with a client who's always sore, let's say they're resistance training, they're always adding more weight, they're always using lots of negatives, they're always sore from head to toe, you might want to think about healthy fats as a calorie source instead of just high carbohydrate diets all the time. The next slide is straight from the Williams book. It's from a slightly older edition, but what this shows is the effects of aerobic training, endurance training on skeletal muscle, and at the top is an untrained muscle. And at the bottom is a trained muscle, and you can immediately see lots of mitochondria. There are more, they are bigger, and you can see the little dots of glycogen that are next to the mitochondria. Now, I showed you a real picture of that from a muscle histology slide, but here's a cartoony version where you can see there's glycogen dots. You store more glycogen in your muscles when you're fit. And also you can see there's little triglycerides, there's little oil droplets that are next to the furnaces as well. So we want some of those for fuel, obviously, but just not tons and tons.
So there's a little bit more of the textbook version of an intermediate class talking about carbohydrate use in the body, particularly with athletes, how you could greatly expand stores, some of the actual looking inside the body, microscopes looking inside the body and see how this stuff happens. It's fascinating stuff, but we're going to call it there, and we'll finish this next week with a part 3. The NutritionRadio.org podcast is for informational purposes only. If you're interested in starting a diet or exercise program, check with your physician, nutritionist, or qualified exercise physiologist in order to make the progress that you need.